In our final section this year, we're going to talk about acids, bases, and salts. One thing we've learned is that acids, bases, and salts are all electrolytes. What's an electrolyte then? Well, a compound that if you put it in water will conduct an electric current. Pure distilled water does not carry an electric current at all. It's the things in it that can do it, and we classify those as electrolytes. Now, let's look at our definitions of acids and bases. We've been using pretty simple definitions for them throughout the year. The ones we've used are an acid is any compound which begins with H when we look at the chemical formula, and a base is anything not starting with an H. So if you look at acids, there's a couple exceptions. There's more than two, but a couple there is H2O. Well, water starts with an H, but it's not an acid. And then there's this other one, CH3COOH. That's acetic acid. It doesn't start with H. Here, the H that would normally be at the beginning is at the end. And that is actually an exception for both of them because for a base, it doesn't start with an H, but it's still not a base. It's an acid. Off of this slide, write down electrolytes. You may have noticed on the previous slide it said definitions for acids and bases, meaning more than one, and there are several. On this slide, we're going to look at the next one, which is an Arrhenius acid and base, and these definitions came about in the 1880s. Arrhenius is a person, and he defined as an acid any compound which dissociates in water to give hydronium. Hydronium is H+. And an Arrhenius base is any compound which dissociates in water to give hydroxide or OH-. If you look at those two, then H+ and OH- can combine together to make the molecule water. So basically, it's the two things that make up water. And that's how Arrhenius defined acids and bases. Off this slide, just write down Arrhenius acid and Arrhenius base. The next definition of acids and bases came about in the 1920s, and that was by Bronsted-Lowry. He defined an acid as a proton donor and a base as a proton acceptor, and gave us the definition of a proton as an H+, which should make sense to you because if you look at a hydrogen atom, it has one proton, one electron, and 0 neutrons. So if I take away its electron, I'm left with a hydrogen proton nucleus and nothing else, so it's got a +1 charge. And that's how he defined acids and bases. So off this slide, write down Bronsted-Lowry acid, Bronsted-Lowry base, and proton. Later in the 1920s, G.N. Lewis gave us definitions for acids and bases. His name might be familiar to you if you remember drawing Lewis structures where we did the molecules and we put the electrons in and we always paired up the electrons. So everything he tended to do worked with electron pairs, and same thing here. A Lewis acid is an electron pair acceptor and a Lewis base is electron pair donor. Off this slide, write down Lewis acid and Lewis base. Our fourth new definitions for acids and bases came in the 1930s and 40s. So you're dealing with the period of the Great Depression leading up into World War II and part of World War II. So we have the solvent system. A solvent system acid is any compound which, when dissolving in a solvent, increases the concentration of the cation of the solvent. So every other definition would be the solvent is water, and it works here too if it's water, but what if you don't have water? So we are talking about increasing the concentration or the amount of the positive ion in the solvent. Any solvent system base is any compound which, when dissolving in a solvent, increases the concentration of the anion or the negative ion of the solvent. Off this slide, write down solvent system acid, solvent system base, cation, and anion. Our fifth definitions for acids and bases was given to us by Lux Flood, and he was dealing with molten ionic compounds. Ionic compounds have really high melting points, so we're dealing with stuff really high temperatures. For example, table salt melts at over 700 degrees Celsius. That's more than 7 times the boiling point of water. So we're talking pretty high. So he defined an acid as an oxide acceptor and Lux Flood base as an oxide donor. Off this slide, write down molten ionic compounds, Lux Flood acid, Lux Flood base. Our final definition of acids and bases really is not new. A Soviet scientist in the 1950s combined all their definitions, and you're never going to forget how to pronounce his name. It is pronounced Usanovich. A Usanovich acid dissociates from water to give H+. It's a proton donor. It's an electron pair acceptor. Increases the concentration of the cation of the solvent. It's an oxide acceptor. And the last one's a little newer. It's an electron acceptor. It doesn't have to be in a pair. Then you have the Usanovich base, dissociates in water to give OH-, proton acceptor, electron pair donor, increases the concentration of the anion of the solvent, it's an oxide acceptor, and finally is the electron donor. So he's saying they're all correct. Which one do you use? Which one fits your situation the best is the one you will use. Those last two, the electron acceptor and electron donor, is what we use in reduction oxidation reaction chemistry or redox reaction chemistry. Off this slide, write down Usanovich combined all definitions. Of all those previous definitions for acids and bases, one that is very useful to us is Bronsted-Lowry, because from his definitions we can create conjugate acids and bases. In other words, the opposites. So what is a conjugate acid and base? Well, conjugate acid is when a base acquires a proton from an acid. So we're taking something that's a base and it's gaining that H+. The conjugate base is the particle that remains after a proton has been released by an acid. So you take something that's an acid, take away the H+, and we have what's called the conjugate base. In other words, we remove an H+ to find the conjugate base, we add an H+ to find the conjugate acid. And that can be looked at from that diagram at the bottom here. If I take H3PO4, that is an acid, that's phosphoric acid. To find the conjugate base, I remove an H+. So that means I'm taking away an H and taking away a plus sign. So my H's go from 3 to 2, so we get H2PO4, and then I get a minus charge because I took away a plus sign also. From H2PO4, I can also find the conjugate base of that. So again, take away another H+. So I get HPO4 with a minus 2 charge. Yep, you can take away the third H and you get PO4 with a minus 3 charge. That's going from left to right. Now if I go from right to left, if I add those H pluses in, it would be finding the conjugate acid of the particle on the right. Off this slide, write down conjugate acid and conjugate base. Now let's talk about the different kinds of acids there are. Really, there's two kinds, binary acids and ternary acids. Binary acids contain only two elements, one of which is usually hydrogen. And then the ternary acids contain more than two elements. You got hydrogen and two other nonmetals. If one of those other nonmetals is oxygen, we classify it as an oxoacid. There are 6 strong acids. 3 are binary, 3 are oxo or ternary. The binaries are hydrochloric acid, hydrobromic acid, hydroiodic acid. And the oxoacids are sulfuric acid, nitric acid, and perchloric acid. And there's one more in each column that's almost a strong acid, but it's not. The binary almost strong acid is hydrofluoric acid, and the almost oxo strong acid is dichromic acid. Off this slide, write down binary acids, ternary acids, and then just the words 6 strong acids. You do not need to list the acids. Here's what that means. That part in brackets happens first. Every chemical reaction could be classified as an acid-base reaction. But if all the chemicals are basic meaning a pH higher than 7, you take the weakest one of those bases and say, all right, I know it's a base, but it's going to be my acid. Now I'm going to take the conjugate base of that base, and I get a really strong base. That's how we create other strong bases. Off this slide, just write down strong bases, soluble hydroxides. Let's do a little review on how acids get their names, so the nomenclature of acids. I can hear some of you groaning, even though I've recorded this well before you're listening to it. The binary acids, we put a prefix hydro with the nonmetal name, and then change the ending of the nonmetal to ic, and finally add the word acid. For example, HCl is a binary acid. Cl is chlorine. We're going to put a hydro in front of it and change chlorine to chloric, so it'll be hydrochloric acid. The ternary acids do not use the prefix hydro. That's how we can distinguish between binary and ternary. What you do is you look at the polyatomic ion name. If it ends in ATE, you change it to IC. If it ends in ITE, we change it to OUS or OS. And finally add the word acid. So let's take two polyatomic ions, sulfate and sulfite. So sulfate will become sulfuric acid. Sulfite will become sulfurous acid. We have a couple of unique compounds with acetic anhydride and basic anhydrides. An acetic anhydride is any oxygen-containing substance that will produce an acid when dissolved in water. And a basic anhydride is any oxygen-containing substance that will produce a base when dissolved in water. And anhydride, remember, is just meaning there's no water. So if it's acidic anhydride or basic anhydride, these are substances with no water at all. It's been removed. Now, acid-base behavior. The metals on the left side of the periodic table, meaning left of that staircase, tend to form bases. The nonmetals, those above the staircase, tend to form acids. Then there's some strange substances that are amphoteric, meaning can act as either an acid or a base. For example, water. And most things that are amphoteric have that pH really, really close to 7, if not at 7, like waters. Off this slide, write down the three terms: acidic anhydride, basic anhydride, and amphoteric. The last thing we're going to talk about with acids and bases are their strengths, and it's easy to tell them apart. Strong acids will completely dissociate when put in water, or break apart totally into their ions and stay that way. Weak acids do not completely dissociate in water. They only partially dissociate. That means I put it in water, some of it will make ions, some of it will stay together. Strong bases are the same way. Strong bases completely dissociate into positive and negative ions. Weak bases only partially dissociate into positive and negative ions. We also have some things called polyprotic acids. Poly means many, protic means protons. And remember from Bronsted alloy, proton is an H+. So many H pluses. So polyprotic acids contain more than one ionizable hydrogen. If it has two, like sulfuric acid, H2SO4, it will be diprotic. If it has three ionizable hydrogens, like phosphoric acid, H3PO4, then it's a triprotic acid. Off this slide, write down diprotic acids, triprotic acids, and polyprotic acids. We spent the last 13 slides talking about acids and bases. You may remember from the beginning, it was titled Acids, Bases, and Salts. And we're going to get to salts here, and it's really short. Salt is defined as a crystalline compound composed of the negative ion of an acid and the positive ion of a base. So if you look at our example there, I've got an acid and a base. NaOH plus HCl. NaOH is the base, HCl is the acid. So I'm going to take the negative ion of the acid, Cl, and the positive ion of the base, Na, put them together, and you make a salt. And in this case, it's NaCl. Your other product that you get in an acid-base reaction besides salt is always water. So what I'd like you to write down on this slide is salt and water. And that ends this section. We will take a open notes quiz over this next week.